And this is a psychometric chart. We have the psychometric chart. X-axis is the dry bulb temperature, that is will be in degrees Celsius, and wet bulb temperature is an inclined line. The total enthalpy will be H1, H2, H3 line, and saturation flow. The specific humidity will be in the y direction at particular temperature, that is dry bulb temperature and wet bulb temperature meets at a particular point. At that particular point, the right towards the right, the specific humidity can be determined. Based on that, the saturation curve, the saturation point will be determined. Next, draw an inclined line from the point 1 to 2. Read enthalpies and specific humidity values at the point 1, 2 and 3 from psychometric chart. At point 1, enthalpy is equal to 16.5 kilojoule per kilogram. At point 2, enthalpy is equal to 28 kilojoule per kilogram. Mass of the air is equal to Ma is equal to PV divided by RT. Mass of the A is equal to 100 into 45 divided by 60 divided by 0.287 into 283, which is equal to 0.923 kilojoule per second. Heat that is added is equal to Q is equal to M into H2 minus H1, which is equal to 0.923. That is, the mass of the air is equal to PV divided by PT. Ma is equal to 0.923 kilogram per second. Heat that is added can be determined by using the formula Q is equal to M into H2 minus H1. A value of M is 0.923 into H2 is 28 minus H1 is 16.5. So the value of Q will be equal to 10.615 kilojoule. Next, mass of the air is equal to 0.923 kilogram per second. Heat that is added is equal to 0.923 into 28 minus 16.5, which is equal to 10.615 kilojoule. Next, the specific humidity is equal to 0.003 kilogram per kilogram of dry air, which is equal to 0.012 kilogram per kilogram of dry air. The moisture that is added is equal to 0.012 minus 0.003, which is equal to 0.009 kilogram per kilogram of dry air. We know that the specific humidity omega is equal to mv divided by ma. So we have determined that moisture added is the omega value, which is equal to 0.009 equal to mv divided by ma. The value of ma is mass of the air 0.923. The total mass of the stream will be equal to 0.0083 kilogram per second. Next, mass and energy balances. So the outline is the terminology: the specific heat, enthalpy, heat, sensible heat, latent heat, saturation temperature and pressure, saturated liquid and vapor. Phase diagram of water, liquid, that is liquid and vapor phases. Subcooled liquid, condensate stream, saturated stream, that is a mixture of condensate and vapor, vapor and superheated stream. We have to determine stream table, steam quality, superheated steam, energy content, that is liquid products and the steam. Mass and energy balances, batch and continuous process for mixing and heating, direct and indirect contact heating, indirect contact cooling, and determination of the steam quality. Next, first we have to see about specific heat. The specific heat is represented by a symbol Cp, which is equal. The unit is joule per kilogram Kelvin. That is, specific heat is defined as the energy that is required to raise the temperature of unit mass of a substance by a unit value. It varies with temperature. However, for approximate calculation, Cp of water is assumed to be 4180 joule per kilogram Kelvin. Enthalpy is represented by H and its unit is joule per kilogram. Heat content of a system. It is always expressed relative to the reference state, usually 0 degrees Celsius. Generally, enthalpy is assumed to be 0 at 0 degrees Celsius. For most liquids, enthalpy will be in Cp, that is determined in temperature of degree Celsius. Next is heat. Heat is represented by a symbol Q, that is mentioned in a unit of joule, that is defined as energy transfer due to temperature difference between the system and the surroundings. When energy is transferred, it is represented per unit time, its unit or joule per second or watt. The energy transfer may be utilized as a sensible heat or latent heat. Next, sensible heat. Sensible heat is defined as the energy transferred from hot to the cold object. For batch systems, Q is equal to mCp delta T. For the Q will be in J and Q is in joule per second, or it is in watt. For continuous system, Q is equal to mCp delta T. For latent heat, Q, the energy transferred during the phase change without any temperature system. This is given by Q is equal to m lambda. M will be in mass and Q is in joule and Q is in joule per second or watt. Next is latent heat of vaporization. Latent heat of vaporization is given by lambda vaporization. Energy required to convert 1 kilogram of liquid to vapor phase, that is temperature changes. It equals energy released when vapor condenses to liquid at the temperature. For heating food, the energy of condensing steam is made use of the latent heat of vaporization at 100 degrees Celsius, which is equal to 2257.06 kilojoule per kilogram. Next is latent heat of fusion. It is represented by lambda fusion, that is J divided by kilogram. The energy required to convert 1 kilogram of a solid to solid phase at temperature changes. Next, phase diagram of water. The phase diagram is given, it is plotted between pressure and the enthalpy H. Within the dome, that is the curve, water exists as a steam, which is a mixture of liquid and vapor. Here the temperature and pressure are the constant and are called as saturation temperature and pressure. Left of the dome is known as subcooled liquid. Within the dome it is known as the saturated steam, and right to the dome it is represented as the superheated steam. This is a saturated steam table. Here the lambda vapor pressure, that is atmospheric pressure, which is equal to enthalpy at atmospheric pressure minus enthalpy of C at atmospheric pressure. 2676.1 minus 519.04 is equal to 2257.06. Next, steam quality. A term steam generally refers to the saturated steam, not a superheated steam. Steam is a mixture of liquid, that is condensate, and vapor. The enthalpy of the steam is weighed mean of enthalpy of a condensate Hc and the enthalpy of a vapor Hv. Hs is equal to x into Hv plus 1 minus x, which is equal to Hs minus Hc divided by Hv minus Hc. Rearranging that, when x equal to 0, when Hs equal to Hc. Note that x equal to 1 when Hs equal to Hv. Also, higher the steam quality, higher the value of the Hs. 0 less than or equal to x less than or equal to 1. 0% less than or equal to x less than or equal to 100%. Here, Hc and Hv at saturation temperature and pressure are determined from steam bubbles. For superheated steam, when the temperature of the vapor is greater than the saturation temperature, at its saturation pressure, the steam is referred to as superheated steam. The difference between the steam temperature and the saturation temperature is the degree of superheat. Superheated steam temperature at a given pressure can also have different temperature greater than the saturation temperature, unlike saturated steam. Thus, to define the state of superheated steam, one has to specify the temperature and pressure. To determine the state of saturated steam, one has to specify the either temperature or pressure. Next, Q versus T. It is represented versus Q versus T. Q, that is energy supplied, and temperature, that is in degrees Celsius. Here the sensible latent heat is S to L, and L is latent to sensible, that is sensible, and L to V is latent to sensible. Next, energy content. The thermal energy content of a solid or liquid T Kelvin minus 273 or mCp into T Celsius minus 0. This is based on the assumption that the energy content of the substance is always 0, which will be equal to 273 Kelvin. The thermal energy content of steam is given by ms into hs. Here h is equal to x into Hv plus 1 minus x into HC heat exchanger, equipment where heat is exchanged between two products, steam losing heat and cold product gaining heat, hot water losing heat and cold product gaining heat, cold water gaining heat and hot product losing heat. They may be match or continuous and direct or indirect contact. Batch heating, home microwave oven, direct contact heat exchanger, mixing steam with milk in the making of cappuccino, continuous heating, steam injection or infusion of a flowing product. Indirect heat contact heat exchanger, batch heating, it was for canning. Direct and indirect contact heat exchangers. Direct contact heat exchangers, steam contacts products and mixes it with steam, losses energy as it condensates. Product gains energy rapidly when heat transfer. However, the product is diluted. Next, indirect contact heat exchanger. Steam is separated from the product by barrier, not as much as or a rapid heating. However, product is not diluted. Energy transfer by steam to a product in a direct contact heat exchanger is given by Ms into Hs. Energy transfer by steam to a product in an indirect contact manner heat exchanger is given by Ms into Hs minus Hc. Mass balance overall mass balance equation. The overall mass balance, the total mass going into the system must be equal to the total mass coming out of the system plus the accumulation of mass in the system. Batch system, mass m in kg. Continuous system, mass flow rate m in kg per second. uh, Component mass balance. For any component in a system, the total mass of the component going into the system must equal the total mass of that component coming out of the system plus any accumulation of a component in the system. For any system or subsystem, the number of mass balance equations is equal to the number of components in the product. One mass balance equation can be written for each component. Next, energy balance. Energy balance for any system, the energy going into the system must equal the energy coming out of the system plus any accumulation of the system and of the energy in the system. Any one energy balance equation is written for any system or subsystem irrespective of the number of components in the product. One mass and energy balance equations are written. Make sure that the number of equations and number of unknowns should be equal. Next, applications of the mass and energy balance. Mixing and separation of streams of product with different composition. Condensation of steam outside a tube through which product flows. Mixing of steam with the product. Direct contact heating is faster than indirect contact heating. Side effect or direct contact heating is dilution of the product. Next, mixing of two products is a batch system at the same temperature. Here M1 and X1 is a product 1 and M2 at mole fraction of X is the product 2. After a particular time mixing, M3 and X3 will be the total masses of the stream 3 and the solid fractions of the 3. The total water balance equation is however not a totally new equation. It can be obtained by subtracting the total solids balance equation from the overall mass balance equation. Thus there are only two equations for the above system. Hence, given any four variables in the system, the other two variables can be determined. Note that the six variables in the above system M1, M2, M3, X1, X2, X3. Also there is a system such as known as X1 plus X2 not equal to X3. Say based on this, that is for two different products, the specific heat of that product will be varying after a particular time. After mixing, the specific heat of the particle 3 will be changing. Is direct heating with the steam. Direct heating, that is using a continuous steam. The cold product will get a particular pressure and it will get out as a warm diluted product. Here M, X and CPT, mass flow rate, solid fraction, specific heat, temperature respective, subscript F for feed and P for the product. Next, determination of the steam quality. To find the determination of the steam quality, we are using a flask here. Here HV and HC being determined from steam tables, and MCPT mass specific heat temperature respectively. Subscript C for the gold and H for the hot. At the absolute steam pressure of P or the steam temperature of T, thus X equal to Hs minus Hc divided by Hv divided by Hc. Next, a summary of the mass and energy balance. Energy of the liquid is equal to mCp T, that is in degree Celsius. Energy of the steam is Ms and Hs. Saturation steam tables. Steam enthalpy of a condensation Hc and the vapor is Hv at various saturation T, the various saturation of temperature and pressure. Steam quality, it is a measure of the amount of steam in the vapor form. It ranges from 0 to 1 or 0% to 100%. Calculations for direct heat using steam. Overall mass balance. Steam is a part of a overall mass balance equation. For energy balance, no need to factor the energy of steam on RHS of the equation. Calculations for indirect heating using steam. Overall mass balance. Steam is not a part of the overall mass balance equation. Energy of steam as it exists in the system has to be included on right hand side of the equation. Thank you.